What's up, Algebros? In this video, we're going to find the zeros of the following polynomial function. So here we have f of x equals x cubed minus 2x squared plus 9x minus 18. As always, remind yourself of the concept here. We're trying to solve the equation f of x equals 0. So we'll take that degree 3 polynomial expression and set it equal to 0 and do our best to solve for x. Your first attempt at this should always be to try and factor the polynomial by hand. You'll notice this polynomial expression on the left has 4 terms, so you could try factor by grouping. And I'll let you in on a little secret. This polynomial actually does factor by grouping. However, I would like to show you how you can find the zeros using the rational zeros theorem and so on and so forth, because there's going to be a lot of different concepts that I can fold into the solution if we do it that way, which I think is good for us educationally speaking. Alright, so I'm going to pretend that it doesn't factor by hand even though it does, and proceed to do the rational zeros theorem. Alright, so in a lot of cases these polynomials won't factor by hand using the grouping technique, so this is something you'd have to do anyway. Remember, that's going to require 3 lists. It's going to require a list of the factors of 18. That's our list for p. So numbers that go into 18, including the negatives, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, plus or minus 18. And then there's a list for q, which the list for q comes from the divisors of the leading coefficient, which is a secret ninja 1, so plus or minus 1. Therefore, the list for p over q, keeping in mind that these guys represent numerators and these guys here represent denominators, our list for p over q is going to basically be the same list as p, since the denominator of each of these fractions is 1. But I'll write it out anyway. Plus or minus 1 over 1, plus or minus 2 over 1, 3 over 1, and so on and so forth. So let's see, we have 12 total fractions in the list for p over q. Keep in mind that by the fundamental theorem of algebra, there should be a total of 3 zeros. Therefore, not every one of these fractions is going to be a 0. And quite honestly, sometimes it's the case where we list all these fractions and none of them are zeros. So, we'll have to kind of take a look at the polynomial function from a different perspective to narrow this list down if possible, and kind of snuff out some rational zeros if it has any. So what I would do is get your graphing calculator ready, and in y1 we're going to type in x cubed minus 2x squared plus 9x minus 18. We'll see what that looks like in the graphing calculator, and we'll also sketch it out and see what other things that we can infer from its graph. So let me get my graphing calculator up on the screen. In y equals, we'll type in the polynomial function. We'll hit zoom 6. And I'll go ahead and sketch that out in this coordinate plane. Oops. Do that. So something like that. And it looks like there's one x-intercept. So there would be one real 0, and that would imply that there are going to be 2 non-real zeros. It appears as though this graph might be crossing the x-axis at x equals 2. So that's going to be our guess, and that's not a bad guess to make, because if you notice in our list for p over q, 2 actually happens to be part of that list. So what we're going to do with the 2 is some synthetic division. Take that 2, put in a little half box, and then we're going to write out the coefficients of f of x directly to the right of it. So 1, -2, 9, and -18. We'll finish up the synthetic division setup here. Alright, first step of the synthetic division is to carry down the leading coefficient. Then we're going to multiply this 2 by that number to get 2. Add down in column format, we get 0. 2 times 0 is still 0. Adding down, we get 9. And then 2 times 9 gives us 18. And adding those down, we do get a remainder of 0, which of course makes me so happy that I have to draw a dabbing emoji. So this does verify that 2 is one of the zeros. It appears to be the only real 0, which, based on the graph, 2 is the only real 0, meaning that there should be 2 other zeros, in which case are going to be non-real. Alright, so maybe that's something we should take note of underneath the graph. So total zeros, this is based on the degree. Total zeros is 3. Total real, just based on the graph, is 1. And then total non-real is going to be 2. So we're going to have to continue on and figure out just exactly what those other 2 non-real zeros are going to be. And to do that, we're going to factor the function f of x using the results of our synthetic division. So this 2 that's right here, using the formula x minus r, will produce the factor x minus 2, and then these numbers underneath the equal bar in synthetic division give us the coefficients of the quotient polynomial. Now do keep in mind the polynomial starts out as degree 3, so this quotient polynomial should be a degree 2 polynomial. And using the coefficients from the synthetic division, we would get x squared plus 9, and that's still set to 0. Now we've gotten to a point to where one of our factors of the polynomial is quadratic, so what we can do is set each factor equal to 0 and solve for x. Doing that with the first factor, we get x equals 2. And then setting the second factor equal to 0, bounce the 9 over, we get x squared equals -9, and taking the plus or minus square root of that is going to give us plus or minus 3i. So there we have it. Those are the other 2 zeros, and they both happen to be non-real. So I'd like to officially write out a list of the zeros. We've got 2, we've got 3i, and we also have -3i. Now what's really cool about that is these 2 zeros are also conjugates. And that's something to be expected because of the conjugates pairs theorem. One other thing that I'd like to do is build a zero factor table so that we can verify the linear factor theorem. So one of our zeros is 2, then positive 3i, then -3i. So the factor we can build with 2 is x minus 2. The factor for 3i is x minus 3i. And the factor for -3i is x plus 3i due to the double negative. So you can piece these together. We get x minus 2 times quantity x minus 3i times quantity x plus 3i. And you can see that there are 3 linear factors. So that's a verification of the linear factor theorem. And that's where all the pain and fun and excitement for this video ends. Of course, if you have any questions whatsoever about it, feel free to let me know. Otherwise, thanks for watching, and I'll see you guys next time. Goodbye.